Welcome back, everybody. And in this demonstration, we will actually formulate a hypothesis and make an exploratory data analysis. So before I start, I want to point out that I have signed into my ClinEpiDB account. And this is because if you want to save your analysis, even after you have shut down or reset your browser, then you will want to make an account and log in. It only takes a minute to make an account. But if you don't want to save your analysis, you are welcome to continue using the website as a guest. You will still be able to do the analysis. So let's go back to GEMS1, the study that we have been working with all morning. And what I will do now is to sort of read through the study page and come up with an interesting question to ask. So one thing that we do know is that GEMS1 recruited kids that were under 5 years of age. And they recruited kids with diarrhea or with severe diarrhea, and matching controls, which were kids without diarrhea. And then we know from reading the study page that they collected stool samples and tested them for various pathogens. So it might be interesting to explore a few pathogens in this study population, and we might choose 2 or 3 pathogens as examples: rotavirus, cryptosporidium, giardia. Also, sometimes when you're doing an analysis, you may have a particular site that you're interested in. So say we are interested in what's happening in Kenya. And you may be interested in causes of diarrhea in particular age groups, such as infants. And that is something that GEMS looked at. It looked at causes of diarrhea in 3 different age groups. So we could come up with a hypothesis that looks something like this, that in kids from Kenya, aged 0 to 11 months, rotavirus, cryptosporidium, and giardia are present in higher population and stool samples from diarrhea cases as compared to diarrhea-free controls. So that sounds like a reasonable hypothesis, right? So we can go in here and actually maybe name this. Infants. So we could give this a name. And then let's go on and actually subset our data. So we choose the population of interest. What you see here is the pink bars are all representing the entire data set. We can go in here and we want participants only from Kenya. So I'm going to go ahead and subset to Kenya. And what do you see here? You see that the numbers change. Now you see that the pink bars are shorter for households and participants and samples. And that's because we are filtering our data. And now the pink bars are representing only households, participants, and samples from this particular country. So you can see here, it's down to 3,359 communities, or in this case, also participants. And this was a 1-to-1 ratio. The other thing that we want to do is choose our age group. So I'm going to go to this variable age group and choose the infants. So again, what do you see? There's a change in the participant numbers. So Sheena has put up a quick poll here. Can you tell us in our subset that we are interested in, how many participants do we end up with for our analysis subset? We'll give you a few seconds to answer this poll. So our data set diagram is a great way to tell, as you're subsetting the data, are you removing too many, very few? I mean, how many individuals are you left with? It's a great way to tell that as you're doing a subset. So thank you for participating in the poll. And yes, everybody has seen that, you can see right here that we are left with a little over 1,000 participants. So the next thing we will do is identify some variables of interest for our analysis. So we are interested in looking at this in cases and controls, comparing cases and controls. So definitely this would be one of the variables that we are interested in. And it is also helpful to note down what type of variable you have, because that will decide what sort of plot you use to look at your data. So what I see here is that this is a categorical variable and it has 2 levels. It's dichotomous. So some of the other variables that we want to use are down here in the sample that we would like to see pathogens in the stool. So for instance, we want to look at rotavirus in the stool. So that would be here in viruses in stool. And again, we see that this is a categorical variable and it has two levels, presence and absence of pathogen. The other two pathogens that we are interested in looking at are Cryptosporidium and Giardia, again, categorical variables with two levels. So once we have sort of looked at all the variables that we're interested in, now we are ready to go make some plots and test out our hypothesis. So again, we go here and open our menu of visualizations tools that we had seen earlier. And now we need to decide which tool would be appropriate to use for this. And since I'm comparing cases and controls against presence and absence of pathogens, this is the one that I will choose, the 2x2 plot. And this opens a blank plot, and I can go in and choose my x-axis variable, which in this case is case or control participant. And here I will go and look for rotavirus by ELISA. And this is the plot that I get. So from looking at this plot, can you tell if cases or controls have a higher proportion of rotavirus infection? So, yep, thanks for answering that poll. It's easy to tell from looking at this plot, right? That we have, here you can hover over the plot and actually see the proportions as well, that in the case of cases, diarrhea cases, you have about over 20% of cases have rotavirus in their stool. And when you look at controls, it's only about 2%. Now, one thing I will point out here is we give you this plot, this graph, but you also get the numbers in a very typical 2x2 table here. The other thing that I will point out is that you see now that you have the numbers here for your subset. So it's telling you what fraction of the data you're actually plotting here. And this missingness table is another very useful feature where it's telling you of the 1,346 participants that you're plotting, do any have data missing for either variable, the x-axis or the y-axis variable? In this case, they don't, but it's very useful to see if you're plotting something that has a lot of missing data, which would cause some inadvertent bias. So we can name this, we can call this rotavirus and save this plot. I'm going to move this out of the way. And so that's our rotavirus plot. We are ready to make another visualization, a very similar one. In this case, we want to look at a different variable, which is Cryptosporidium by ELISA. And what do we see here? That again, there is an association of diarrhea cases and presence of Cryptosporidium in the stool. 14.1% of diarrhea cases have crypto as compared to only 6.4% of controls. So we can again name this plot, minimize it, and make another one for our third pathogen that we're interested in looking at, which is Giardia. So this is a little bit surprising, isn't it? That we expected that diarrhea cases would have an association with Giardia, but you find that there's more Giardia in the controls. In 12.2% of controls have Giardia as compared to only 9% of cases. So this is a interesting and unexpected result. So what have we done here? In a matter of minutes, we've made 3 plots, all looking at associations of different pathogens with diarrhea cases and controls. And what we have done here is really we've recreated some of the most important findings from the GEM study. The GEM study did find that rotavirus is responsible for a large fraction of diarrhea cases. The good news is that we now have a very effective rotavirus vaccine that is being routinely given to children in Kenya and other parts of Africa and Asia. And looking at this result, we can expect that this vaccine will have a large impact on diarrhea in Kenya. The finding of giardia in the stools of kids that don't have diarrhea was also a finding from GEMS, and it highlights how kids living in fecally contaminated environments often have enteropathogens colonizing their gut, even though they may be asymptomatic. So what I have shown you very quickly in a few minutes by clicking around is we have replicated some key results from an important study. Now, it's important to note that this is strictly exploratory, and it does not at all take the place of rigorous statistical analysis. But it is a great starting point to start understanding the data and to actually see whether it would be useful to download it and work with it more rigorously. So if I go now to my analyses, so to this page up here in the workspace, you'll see two links, My Analyses and Public Analyses. If I go in the My Analyses link, I actually see that our analysis that we just made is saved here. So you can save your analysis as you work in ClinEpiDB. I will also show you the public analyses. The ClinEpi staff has made similar analyses on a bunch of different data sets that we have released. And they're all here for you to look at and explore. So having shown you that demonstration of exploratory data analysis, we would love for you to try your hands at doing this. So what we have created for you is two exercises. One of them is a structured exercise where we really walk you through a particular question step by step, and you can click around and try and do this analysis for yourself. The other one is a set of guidelines for a self-guided exercise that if you wanted to ask your own question of one of the data sets and try to answer it, then we give you some guidelines for doing that. So it's up to you to decide whether you want to try doing an unstructured exercise, a self-guided exercise, or if you want to do a more structured exercise and walk through this. So at this point,